So the first question is, why are we working on BERT? And specifically, we're working within Hugging Face for BERT. So we have kind of an illustration from the original paper, which is, looking at pre-training and then fine-tuning on the task. So let's kind of go through this a little bit. One is that BERT is a very popular model for many NLP tasks. The reason why is that, we start with establishing pre-training on a large text corpus with mass language modeling. So essentially creating this model that generally understands language. And then it allows us to fine tune from there onto many data sets. So many different applications, including question answering, named entity recognition, classification, sentiment analysis. All of those work really well with BERT. And ultimately, this allows us to simplify and expedite getting state-of-the-art results for our ML pipelines, right? So as an ML engineer coming in, trying to create a new application for within NLP, BERT works out really well for being able to simplify that process just by taking that pre-trained model and fine-tuning for a few epochs on our own data. And in the same way, Hugging Face is a very popular framework for NLP. It's built on top of pre-trained models like BERT, making those available, and additionally adding in well-formed pipelines to simplify the engineering work. So we can go from taking that pre-trained model to a deployed model in a much shorter time frame than if we were trying to pre-train this on our own and build out all of these pipelines. So it's additionally what we wanted to plug in, and it's a very popular pipeline for many people. So we want to make sure that we were offering something that most people could plug into with what they're already using. And ultimately, this simplifies and expedites the getting state-of-the-art results for ML applications again. And finally, there are already many sparsification techniques already applied to BERT. So this is something that we wanted to take advantage of and iterate on top of to try and improve and push the state-of-the-art further. So this includes things like PruneBERT, which Hugging Face pushed out. It was a new pruning algorithm that they pushed out with it and created the sparse architecture for BERT to very high sparsities. distillBERT, which explored layer dropping and created very accurate models with much better performance characteristics. And then finally, quantizedBERT, which came out from a partnership between Hugging Face and Microsoft in Onyx Runtime to be able to create these streamlined flows for quantizing BERT and be able to get even better performance. So let's kind of go through these sparsification techniques a little bit. So I mentioned, pruning, quantization, layer dropping. So let's dive into these a little bit. What is sparsification? So it's the process of removing redundant information from a model. So neural networks are very over-parameterized. And what we can do with sparsification is come in and cut away the extra parameters that are in that model, leaving behind a sparse architecture that fits the problem that we're trying to solve. So let's look at what pruning does. So let's take a fully connected network, such as this, so a few different layers, and then weights connecting between them. What we can do is then zero out a bunch of these weights so that we create a not so fully connected network. And the important part here is one, how we zero out those weights. There are quite a few different techniques. We usually use magnitude pruning because if it's given long enough, it will outperform most other algorithms that are out there right now. But one is selecting the weights to get rid of. And then two is figuring out how to speed this up and exploit this. And this is what we'll go through a little bit later. Additionally, quantization. So what is quantization? Well, this is looking at the weight distribution of a specific layer. Actually, in BERT, we're looking at the distribution of the weights in terms of magnitude value that they have. What we can do, though, is take that and also the activations and compress them. So we can take it from a floating point 32 representation and compress that information into an int8 representation. So we can get a 4x reduction in size and generally a greater, at least a 4x increase in compute just by doing this. And ultimately, this kind of works because the neural networks, the different layers, usually aren't learning too complicated of a function. So we don't have to be extremely precise, at least in inference, whenever we're executing this model. So we can get away with actually reducing the precision that we're representing these weights and activations by and exploit that for faster inference. Now let's dive into what is compound sparsification, because that was the title of the talk, and we mentioned that. So it's combining multiple sparsification techniques to achieve better performance. So going through those sparsification techniques that we mentioned earlier, being able to combine all of those to create a better representation of the model. So, so let's dive in a little bit. Let's take a dense network, for example. So that same dense network, what we're going to go through is multiple sparsification stages to be able to create a highly optimized model. What we'll do first is start out with structure pruning. What you'll see is that we removed the second layer here, and we can remove that second layer generally. So if we look at BERT, for example, what distill BERT did is it removed half of the layers. So we went from 12-layer BERT to 6-layer BERT, and ultimately that led to a little bit of a drop in accuracy, but a much greater increase in speed for these networks. So for these networks, there's generally something that we can do to create a structured network here from the original dense network and try and optimize for our deployment problem. What we can see though is that it's still pretty dense in the middle. And what we can do then is actually apply unstructured pruning on top of that. And so you can see that we removed a bunch of the weights within that already structurally pruned network. And finally, what we can do is add quantization on top of that. So taking these weights and these activations and making them smaller so that we can scale it down. And what this leads to is a very compact model that runs much faster, especially whenever we're using something specifically designed for this, such as the deep sparse engine. So let's dive into a few results for this. What does this actually look like whenever we apply it to BERT? Well, let's dive into 12-layer for a second. So this is 12-layer BERT inference performance with an 88.5 F1 on the squad baseline. These models were all trained on downstream on squad, or fine-tuned downstream on squad to create different versions. So we have the original dense version. We have an 80% sparse version, meaning that we removed 80% of the weights with unstructured pruning. Here's the prune BERT paper, which additionally did unstructured pruning. We have dense quantization, so just taking a dense model and quantizing it. And then we also have the combination of unstructured pruning with quantization, create a 70% sparse network. So we can see as we go down and add these sparsification techniques together, that we get much better performance, right? Especially with that small dense bar. So let's look at what those results look like for 12-layer. One note is that prune BERT actually only recovers 92% of the original. The rest of these models laid out at least get to 99% of our original baseline. Actually, the 80% sparse does a little bit better. So one note is that prune BERT is a little bit of an outlier, but we wanted to include it here because it is an active model that's out there right now. So what we can see is that the 80% sparse is actually 3.5x faster than the dense model. And whenever we get down to the 70% sparse quantized model that we created, we can get the 6.4x improvement in dense. And then additionally 2x faster than the dense quantized. So comparing our dense quantized to the sparse quantized. So significant performance improvements already just by looking at the 12-layer. And I should note that all of these results are for throughput use cases, so specifically batch size 32. And all these measurements were done on a C5 12x large on AWS, which we'll go through a little bit later. And then not only is it just performance benefits, we also get a 9x compression in size going from this dense model down to the 70% sparse quantized. So this dense model is around 380 megabytes, and we can get that 9 times smaller just by doing the unstructured pruning and quantization. Now let's look at what it looks like whenever we add layer dropping to it. So we go from a 12-layer to a 6-layer BERT, as we talked about with structured pruning, and then additionally add in unstructured pruning to it, as well as quantization on top of that. So we can see that dense, we're getting about a 2x speed up from the 12-layer to the 6-layer, but the 80% sparse is giving significantly more speed up over the dense as compared, and especially as compared to the 12-layer dense. And finally, the sparse quantized gives even more speed up. So let's run through some of the highlights there. Overall, whenever we look at the sparse quantized model, we get an 11.4x total speed up, right? So a huge speed up over the dense with a little bit of drop in the F1. So ultimately, this comes down to our preferences as ML engineers and data scientists as we're deploying these models. If we think we can sacrifice a little bit of accuracy to save money or to get back to the user faster, then that's a decision that we can make here, right? We can stay with the fully accurate 12-layer, or we can go down to a 6-layer and get an 11.4x speed up over the top of what we might have started with that 12-layer dense. And additionally, it's a 5.8x improvement over the dense 6-layer. So sparse quantized gives almost a 6x improvement over just that layer dropping technique. Additionally, we get to a 13.2x file compression size for the sparse quantize. So, saving even more data movement as we're trying to deploy these models on the edge. And then finally, we have the 3-layer. So taking 12 layer, dropping off 9 of those layers, we get down to a 3-layer BERT. And the baseline gets us to about 80 for the F1 on squad. So we drop a few points of accuracy getting down to the 3-layer. But again, this is an option that we can take to try and get better performance. So the dense gets about a 4x speed up over the 12 layer, but we can see what the sparse quantized number looks like, right? A significant improvement over where we started from. So let's run through those numbers. So for a 3-layer, we can get a 21x total speed up for the 70% sparse quantize. Just a huge number to be able to get to over 1,000 items per second, close to 1,250, right? Originally, we started all the way down at, I think, around 60. We're at 1,250 items per second. And then finally, looking at the file sizes again, we took this 12 layer from 384 megabytes, and after applying layer dropping, pruning, and quantization, took it down to 22.1 megabytes. This is something that's much easier to download on the edge. So I'm going to stop right here because I see a few questions coming in, and we can try and run through. So one of them was, why do you report throughput? How does your technique perform for latency? Batch size equals 1. So it's a great question. Currently, we're optimized for throughput pipelines. This is the latency metrics we do get speed up on, but not as much. And this is something that we're actively working on right now. We're hoping within the next 2 releases to be able to have the same types of speed ups or around the same level of speed ups for these latency use cases. So if you're using throughput right now, this is our main use case that we're targeting. And then latency coming later in a few releases through better support in the deep sparse engine. And then actually what I should mention is that the dense and the dense quantized numbers are measured in Onyx runtime. And then the sparse numbers are measured in deep sparse. So deep sparse being specifically designed for these sparse networks, which we'll run through a little bit later in the webinar. And then let's see, we also have, is there a pattern on performance based on the layer locations? For example, are the final layers more susceptible to loss than the initial layers to drop in the weights? So this is actually a really, really interesting question. Overall, the best results that we found in terms of recovering better for these models whenever we're pruning and also layer dropping is that uniform works best. Movement pruning, the results that they pushed out, that team pushed out, found that they could adjust the weights a little bit, but we did find that just running magnitude pruning with uniform distribution across BERT for a longer training time beat the movement pruning paper. So right now, that's something that we're actively working on, trying to figure out if there's things that we can do to try and localize better to see if there is a pattern that we can discover to try and redistribute the weights a little bit better to recover more. But so far, ultimately, if you train for long enough, the pruning method and the way that you're pruning starts mattering less and less. So it's all about trying to prune over a longer time, and ultimately those finish up right around the same area. And this is some active research that we're looking into right now. So definitely stay tuned with that. We're actively trying to work on a paper around a lot of these topics. So we'll definitely keep the community up to date as we push through that. And then another question, what was the accuracy loss for 70% sparse quantized versus FP32 dense? And was the quantization T-ante? Yes, so quantization that we're mentioning here is always N-tate. Sorry if that wasn't clear. But yes, whenever we're quantizing, comparing these quantizations, it's always N-tate, mainly because that's what the hardware, specifically on CPUs and GPUs, currently support for better speed up. And we're looking at the CPU results here, again, running on an AWS C5 12x large, which has the VNNI instruction set. And then if we're looking at accuracy loss, so we went from 88.5 F1 down to 80. This one gets to within 99% of that 80. So around 79, a little bit higher than 79 for the 70% sparse quantized. So we're looking at a few points of drop here. But again, this is something that we're pushing out, which is trying to match whatever our layer dropped results were, in case people want to deploy for more performance. Ultimately, our goal is within these layer dropped categories, so 12 layer, 6 layer, and 3 layer, come up with models that return close to that baseline, whatever that dense baseline was. and distill BERT being close to that 6th layer. And then again, which backend is the speed up upon? This is all again looking at a AWS C5 12XL. So this is 24 core CPU on AWS. That's what these results were generated from. The sparse results are within Deep Sparse Engine, and then the dense results are in Onyx runtime. So we had a fair comparison between them. And then when unspecified, is the accuracy for the sparsified model the same as the original? Yes, so these are within 99% of the baseline for all these results. All right, and then we also have a question coming in. Do you have comparison to other graph compilers such as OpenVINO? So not currently for BERT, these are numbers that we're working on. In terms of what we've seen, Onyx runtime for the quantized comparison has been giving us the best speed up in terms of all the engines out there right now. But we are actively working on getting OpenVINO numbers. Currently, they push out for BERT large. We haven't seen any numbers push out for BERT, so we're working on a pipeline internally to make sure that we have those comparisons. And then another question, how long does the pruning take? What is a long time? So I'll get into this in a little bit in terms of how do we improve this more. So the current results is that, for example, we'll take something that might have been for squad that was a 5 epoch training cycle. We extend it out to about 30 epochs for that training. So obviously not everybody is able to do that. And there are some future work items that I want to go through a bit later that we'll talk over in terms of how we're going to reduce that training time to make it as equivalent to just taking the original dense network. So definitely stay tuned for that. We'll go through that in a little bit. And then there's another question on there are many BERT models in the Hugging Face library, and what is the difference between squad and other BERT models? So that is a really good question. So there are a lot of different types of BERT architectures that people push up in the Hugging Face. We've seen the base BERT being the most downloaded and the most popular and the most requested for us. So that's what we focus on now. I'll go through a little bit the other architectures that we're going to be targeting. Squad is just one of the downstreams that we fine tune to. So squad is just an example to show that the results work. We could do a few different other data sets as well, like QQP, and then Connell 2003 and others. So these are just fine-tuned data sets that were originally fine-tuned on from the BERT-based model. All right, and then just to clarify, we had another question on the loss for the 12-layer FP32 dense versus the 70% sparse quantized. So what we're getting to for the 70% sparse quantized as compared to the dense is 99% of the baseline. So we're going to end up around 87.8 F1 to try and make sure that we're matching relatively the original squad baseline for the 70% sparse quantized model. All right. Let's see if we had any others that came in. Sorry, I need to just clean these up a little bit. Make sure, let's see. That one, and then there's another question about successfully applying SparseML to many transformer models, but they've noticed that the inputs have to be reshaped before passing into the module exporter. For that specific question, I'd say if you could join our Slack and we can dive in a little bit more in detail. I think this one's very specific to the implementation, and yeah, there's definitely a way that we can get that fixed. So let's definitely talk through that so that you're not having to reshape or transpose for those. And then another question about how does this compare with Hugging Face Infinity? So we're actually getting some results on Infinity. What we can see right now is that Infinity is just using the out-of-the-box engines, and they're trying to optimize for, so doing things like layer dropping. We haven't seen anything where they're actually doing speed up for sparsity. So this is something that we're actually looking at potentially talking with Hugging Face on. so that we can go through and see if deep sparse could plug into infinity as well, or if there's some kind of additional relationship we can do there. So I wouldn't necessarily say this is in competition with infinity. These two could definitely easily merge together as well. And then another question for how portable is deep sparse for ARM or SoCs? Is there a dedicated library that can be used? So this is something that we're actively working on right now that's in our medium term in terms of getting ARM support. Our current support is focused at servers, specifically x86 type servers. So anything with AVX instruction sets and VNI instruction sets specifically for quantized models. And then another good question on, can we use BERT for categorical and numerical features as well? Yes, definitely. So this would also be something that we could go through potentially in the Slack to kind of to point to where those pathways would be. But yeah, BERT is generally a very flexible model to apply to most of these downstream targets. And then another question is the sparsification data dependent? If so, what data was used? So right now we're looking at F1 squad, squad, and specifically the F1 results for squad. We found that in general for fine tuning across multiple data sets, that overall the results hold up very well. That generally we can recover to close to the baseline with these techniques for multiple different downstream data sets that we're targeting, including QQP, Connell 2003, and others. So yeah, generally these hold up very well, and we're actively working right now on extending out our pipelines to make sure that everybody can benefit from those, which I'll go through in a little bit later. So I think that's all the questions. All really good questions, guys. Thank you for bringing these up, and great to go through. So let's go ahead and dive in a little bit more. So let's talk over, we're getting into it a little bit on how do we leverage these results for different downstream data sets or for our own data set. So talking over this, we want to reduce the iteration with recipes. So what are recipes? Well, we encode the hyperparameters necessary for sparsification into these recipes. So whenever we're looking at pruning or layer dropping or quantization, and especially the combination of those, there are quite a few hyperparameters that go into that ultimately can kind of lead to a large combinatorial explosion. So what we work on internally at Neural Magic is trying to encode all these different hyperparameters running through with our intuition, making sure that we can get a very streamlined and optimized recipe, which just highlights, when exactly are we going to be pruning, what pruning levels can we get to, and things like that, so we can push these out so others can use. So we're pushing these recipes up to the Sparsu, which we'll go through a little bit later, so you can pull them down and apply them to your own data set. These are crafted by our ML team to maximize recovery at high sparsities. Again, sparsification can be tricky to get recovery, mainly by tweaking these hyperparams. So this is what's really important on sparsification, is getting the hyperparams right. And it's not always intuitive in terms of the hyperparams needed. So this is something that we work on internally, again, to maximize recovery for these high sparsity models so that we can reduce the compression sizes and increase our performance. And additionally, we test and fine tune all of these across many runs to make sure that these are all working well and going through those iterations internally and pushing out our final results so that other people can benefit from that and plug that into the pipeline. So with that, we have some tutorials to go along with that. For example, for how to walk through, how to apply one of these recipes to your own data set and your own pipeline. And additional examples for deployment and benchmark. So after we create this model on our data, how do we go through to deploy this and benchmark this to make sure that we're getting the results that we expect? So then let's talk through, well, one second, let me just make sure there weren't any new questions that came in. Nothing on this currently. Well, there were, I'm going to save a couple of these for a little bit later that we can go through. Okay. So what's next? What are we looking at next? And this is kind of what I wanted to go into on, again, those recipes can take a little bit longer to run, quite a few more epochs to run on the downstream. But what we want to do is ultimately reduce the time that it takes for you to be able to create these models and make sure that you're not increasing your expense to actually create these models. So what we're looking into right now and actually pushing out shortly is sparse transfer learning. So So what we do is we create a general sparse architecture on the upstream data with mass language modeling. So we take the same training pipeline that was programmed for BERT, and then we apply our sparsity techniques, including later dropping and pruning and quantization, all on this upstream model, so we can fine tune very easily onto the downstream. And the downstream times are right around the exact same time as you would get for dense fine tuning. So essentially, we can transfer these lottery tickets to other downstream tasks. So plugging in exactly as you would use BERT now, but taking those models and making sure that we preserve that sparse lottery ticket that we found that applies to all these different data sets to these downstream tasks, and you can use those from there. So sparse versions of the upstream trained BERT will be available on the Sparsu for anyone to pull down and fine tune onto the data. So stay tuned for this. We're hoping to actually make a big announcement on that soon, so that we can have these results pushed out and anybody can use these. Additionally, we want to push into more data sets and more models. So ultimately make sure that there are example APIs for the different data sets that everyone's working with and different models that everyone's working with, right? At least the most popular ones. So talking over models, we're looking at T5 and GPT-2 currently for generation tasks. There are also some other variants of BERT that we're looking at, such as mobile BERT and others. And then additionally looking at more downstream data results. So for named entity recognition, sentiment analysis, classification, question answering, and more. So specifically getting to T5, for example, looking at summarization and translation, GPT-2 looking at text generation, all kinds of things. Ultimately, our goal is to have these different models pushed up to the Sparsu, so everyone can sparse transfer learn from those, and then deploy those for performance on whatever your architecture is. And one kind of quick call to action here is to let us know if there are any specific models or data sets that you'd like to see. We're actively iterating through this, and any feedback that we get from the community helps out a lot in terms of where we're focusing our efforts on. Okay. So stop there for a second. And let me just see if there is anything else. Okay, so yeah, let me run through these real fast. Sorry, let me click through. Let's go back to here before we dive into the walkthroughs. So just some quick questions. Remember, we're looking at the F1 scores. There was a question on if this squad V1 or V2. This was on V2 currently. And then, sorry, messing up on that. There we go. How long does the sparsification process take? So again, this is going to be data set dependent. Our goal is ultimately to make it so that the sparsification process matches very closely to what your dense training time would have been. And this is ultimately through sparse transfer learning. Currently, if you were to create these models on downstream, we'd estimate somewhere around probably in the range of 3x what the original training time was for specifically for NLP. For image classification and more computer vision is a little bit easier to apply these to, so it takes less time for those. This is something we're actively researching as well, though, such as applying different pruning techniques to try and reduce that time on the downstream. Actually have some really interesting results where we're getting to about a third of the time that we currently are out right now. So stay tuned for those results as we push those out in the next few releases. Another question is, did you benchmark against TensorRT? So we haven't looked at these models on GPUs currently, mainly because what we've heard is that most of the deployments for BERT are on CPUs. So this is where we're targeting, trying to make sure that we got significant speed up for what is state of the art out there on CPU inference engines. And this is what we're focused on right now. We definitely will, as we improve our techniques, be looking more and more at comparing to GPUs and other accelerators. So stay tuned for that. We're actively working on getting those benchmarks both across as many CPU inference engines as we can and GPU, and TensorRT definitely being the top one on GPU. All right. And then another quick question was fine tuning on the NER or classification task should also be possible. And what is the difference in doing this versus the QA tasks that you've already done? So whenever we're talking about sparse transfer learning, these will be essentially exactly the same in terms of fine tuning. Whenever we're looking at the sparsifying on the downstream. This is where it can be a little bit different, where we might want to shift the number of epochs we're running a little bit, but overall the recipes are very transferable across these data sets. We might want to tweak the number of epochs we run a little bit, but in terms of the rest of the hyperparameters, those all stay consistent. So for the different downstreams, such as NER, classification, squad, which is question and answering, or sentiment analysis, all these stay very, very similar. In terms of the flows, we just give it a different data set and use different API for these different ones. And then another question is, do you think the sparsification techniques will work with smaller BERT-like models like TinyBERT or distillBERT for multi-label classification inference? So multi-label classification, we're actually going to be pushing out results on for this specifically. And one quick thing is we haven't looked at TinyBERT yet, but whenever we look at distillBERT, actually, let me run back through this real fast to our results. So distillBERT is actually the 6-layer dense right here. So we can see that essentially what we did is we took distillBERT's results and improved on those with our 70% sparse quantized. Sorry, I should have kind of marked the dense as distillBERT as well. But just wanted to call that out, which is that distillBERT is directly comparable with the 6-layer, and I believe there's a 3-layer version as well. But our results are outperforming the distillBERT results in terms of creating the layer drop models, as well as creating these sparsified models on top of that. TinyBERT is definitely something on our list, including MobileBERT, that we'll be looking into more and more as we iterate through this, through the NLP landscape. So yeah, thank you guys for all these great questions. So let me go ahead and get back up. So let's go through some walkthroughs. And I do apologize because I'm having some VPN connection issues, so I'm not going to be able to go through an exact demo on this. It's one of the unfortunate things about working from home. Sometimes we do have connection issues, but we will be going through and looking at, what did we push up and how can you go about using that to try and make this more concrete. So let me get out of this. And let's go ahead and dive in a little bit. So one thing to point out is that on the Sparsu, we have a getting started page with BERT that we're actively updating as we push more models out and as we push more examples out. You can additionally, we'll call this out later, but you can additionally go to neuralmagic.com/BERT, and it'll take you to the same place. So this is where we're congregating everything under. So there are examples for benchmarking, an example application to run, example deployment, as well as applying a recipe. So let's go ahead and start out with the sparse training first, specifically applying a recipe. So if we're going to go into that, what it'll take us into is an integration within SparseML. So SparseML, we're integrated with the Hugging Face Transformers library. And this is how we go about creating the model. So what we do is we take all of the intricacies of SparseML and the high-level APIs, we add those few lines of code into the Hugging Face Transformers repo for the different example scripts, as well as a higher level trainer class, so that you guys can come in and ideally take that, either run the scripts or take the trainer and plug it into your own code and benefit from all these pipelines and be able to apply recipes. So within here, we have a tutorial on how to sparsify BERT using recipes. So let me go ahead and open this one up. What we run through is essentially how to go through and run these recipes on your own data. So this one runs through specifically Squad. What we do is we create a pre-trained teacher model. So we do apply distillation for all these models. Distillation does help out quite a bit for whenever we're creating these print models. It's not a necessary step, but it definitely helps with accuracy recovery. So what we'll do is we'll create a pre-trained teacher model. This is very similar to distillBERT for that. And then what we'll do, and what you would normally do if you are doing any kind of distillation or trying to create a highly performant model. Then what we'll do is apply the recipe. So we have a recipe argument on the transformers examples, question answering, for example, as well as a few different other examples, which we call out in here. And you can run this command. Don't let all the arguments scare you. A lot of these are very specific to Hugging Face and doing like different save strategies and stuff. But so don't let the arguments scare you. Ultimately, what we need is setting the distillation and then setting the recipe. So we'll run that, create that, And essentially what we'll end up with are results that look like this. And, at least for question answering, you can plug in your own data set here. Additionally, we have other pipelines that you can go through, such as classification. And we're working on NER right now, so that you can plug in your own data sets for that as well. And then finally, we want to export this for inference. So for the deep sparse engine, which we'll go through next, we take in an ONNX format. So what we do is set an ONNX export path so we can create the proper ONNX model. What this will actually do is go through and optimize the ONNX graph, especially for the quantization case, so that so we can create this highly performant ONNX model that's ready to go for deep sparse. So welcome any feedback on this. This is just kind of a quick run through on what we would do if we were training. Additionally, all of these results are pushed up to weights and biases if you'd like to see. And this is actively where we're pushing all of our results as well anytime that we're creating any of these models. So what we end up with here is a model ready for inference, and we can plug it into the deep sparse engine next. So what we can look at is, in terms of sparse inference, we have benchmark, example application, example deployment. All of these are going to take us to our integration within deep sparse, or sorry, an example under deep sparse for Hugging Face transformers. So we have a pipeline built out on top of it for inference, so that you can take the ONNX model, plug it in, and be ready to run with it. So let's look at what a pipeline example looks like. So we can say that we want to do a QA pipeline, and we set our task, set the model path to wherever we save that ONNX file path to, or we can pass in one of the Sparsu files that will automatically download in case you want to do this very quickly. And then we can just run it through. What's my name? And my name is going to be answering back with Snorlax. So this is a quick pipeline example. And the benchmarking example is honestly the most fun, at least for me, because this is where we generated all those results from. So all the results that we pushed out were generated through this benchmarking example. There's a benchmark.py, super simple to run. We welcome everyone to try and spin this up on a compatible CPU on an x86 machine and see what your results look like. So we can push up, we'll just do benchmark.py. You'll see that we have a model stub here. The model stub represents how to get it from the Sparsu, which I'll go through in a little bit more detail in a second. But we just pass in the stub that we want, and then additionally the batch size. Again, batch size 1, you'll see a little bit of speed up on. Batch size 32 is where the most speed up is currently, and batch size 1 is something we're iterating on right now to get better performance and try and match our batch size 32 speed up results. And then finally, you can find a few quick stubs here if you want to try and run these, or additionally, we can go through the Sparsu, where we have a bunch of models pushed. We're actively working on cleaning this up to reduce the choices. But for example, if we wanted to run a prune quantized 6-layer, we can load this really quickly, hopefully. There we go. And we can copy this stuff right from here. So we'll copy that, and then we can plug that right into the benchmark.py script so that we can start running that model. What that'll do is automatically download that model for the Sparsu, create sample inputs, and begin running benchmarks so you can see what the performance looks like. And ultimately make sure that the performance matches what you would expect on your machine. All right, so let's see if we have any questions on this. Another question, actually. So yeah, people are very engaged in the community, which is great. So there's a question about noticing that a distillation modifier was recently made. And is there a tutorial on how to use this? So yes, this is something that's not officially supported yet that we pushed into our open source code base on SparseML that's available on the nightly currently. This is something that's a target for our next release coming out mid-October to have the distillation modifier. And our goal is, if we look back at this example for walking through recipes, is we're actually working on getting rid of the distillation arguments. So in terms of this, we will have an example that comes out with this with the next release. If you want to try and use it beforehand, please join the community, and me or one of our ML engineers are more than happy to jump on with you and walk you through how you might go about using it right now. I should note that it's not fully tested yet since it's not marked in the release, but this is something that's actively available, and we can run you through how to go about using that. But our goal is to encode all these parameters, including the distillation, into these recipes, so it's as easy as just plugging in a recipe and running, and you don't have to worry about anything else. And then there's also a question or at least a comment about what it would be great to have some notebook examples. So this is definitely something that we're actively working on right now. We want to get a lot of this stuff up into Google Colab. So stay tuned for that. If you have any examples that you really enjoy right now, please feel free to send those over, and we'll be more than happy to work on that. And then finally, just a request to send out the links. So we will be sharing all these links as well as the recording and the presentation with everyone afterwards. So definitely don't worry about that. We will be sending those out. All right, so go ahead and dive back in real fast. So yeah, thank you guys for listening and joining in. And next steps, visit neuralmagic.com/BERT to try it out. This will actually get you to all the links that I just went through. So you can go through those. We'll also be sharing these out afterwards as well, including the slides and additional links. We're constantly building at github.com/neuralmagic. So this is where all of our open source code is pushed to. If you have any suggestions or any issues, please go through and file them there. We'll get back to you quickly on that. Additionally, you can join our community, again, on Slack and Discourse. So feel free to dive in there. And this is where we definitely recommend if there are questions that you have, we'll go through and go through and answer you there. And then if you'd like any help with your deployment or just in general sparsifying models, please feel to reach out to our contact form so you can go through and we'll put you in our pipeline and get back to you. Because one thing I should mention is that we're actually looking for design partners. So if your organization has a deep learning project bound for deployment that would benefit from collaboration with us, either on creating these sparse models or deploying these models, ultimately, if you have a use case in computer vision or NLP that you want to speed up, specifically on CPUs or just in general, let us know. And if you have feedback on our product experience, our website, or more, and want to contribute it to us directly. So we definitely want to hear from everybody. Please reach out to Kirsten, who I think we have on right now. Kirsten, I don't know if you want to say hi real fast.
Yes, hi everyone. Yeah, as Mark said, you can reach out to me directly. My email's right there. Would love to chat more with you.
Awesome. And yeah, so we left a little bit of time afterwards for discussion. More than happy to stay on. We have about 10 minutes, actually 12 minutes left for any additional questions that anybody wants to go through.